So we're in section 5.4. So the Pythagorean theorem at this, now it's almost, when we think of the Pythagorean theorem, it's almost like a mantra. What do we say when we're thinking of the Pythagorean theorem? A squared plus b squared equals c squared. We've heard it enough, we've seen it enough that when we think Pythagorean theorem, we think a squared plus b squared equals c squared. We're gonna be a little more precise than that, and we're gonna go into a little more detail. So, and at the end we'll explain what the Pythagorean theorem has to do with this nice picture. So we're going to say, for any right triangle, there's one whole page in there that has Pythagorean theorem. For any right triangle, with side lengths A and B, and hypotenuse C. A squared plus b squared equals c squared. And what do we mean when we say right triangle? What are we saying when we say that? It forms a right angle. One of the angles is a right angle, and a right angle is 90 degrees. So our triangle has to have a 90-degree angle. And which side of the right triangle is the hypotenuse? The longest. Hypotenuse is always the longest side. So I'll draw our picture, and we'll label a picture here. So let's grab a triangle. There's my 90-degree angle. We'll call that side C. It's the longest side. The A and the B sides, it doesn't matter which one is A and which one is B. We can switch those around however we want. This side is the hypotenuse. And another way to remember which side is the hypotenuse is the longest side. It's also the side that is across from the 90-degree angle. So we're across a triangle from the 90-degree angle. So again, something that we've seen quite a few times. We've worked with it. We've done math box problems that have to do with the Pythagorean theorem. So something that we're somewhat familiar with. The Pythagorean theorem is kind of like, yesterday we talked about pi a little bit, and what an important number it was, and how long people have been working with pi. The Pythagorean theorem, they found tablets from as far back as 1700 BC that had sets of numbers that work in the Pythagorean theorem. So as far back as 1700 BC, people were writing down these numbers that work in the Pythagorean theorem. And this was in ancient Babylon. So, and like I said yesterday, back in those times, the reason that things like this were important is because they measured their land, they measured property. So they knew that when you have a triangle, a right triangle, that this a squared plus b squared equals c squared works. So it's been a really important thing for thousands of years. And to me, whenever you have something like that always works no matter what, it's like getting a peek at kind of the secrets of the universe, the way the world works. So it's a really kind of a cool thing. And the Pythagorean theorem turns up in all kinds of places in math. There's so many things that are based on the Pythagorean theorem that it's really It's a really one of the most important equations in all of the world. So it's a really a pretty cool thing. So let's look at a couple of examples of working with the Pythagorean theorem. I'm not sure all of your examples will fit in your flip book. You might want to write examples down in another place. But the examples are not too hard, not too bad. They're like problems that we've seen before. So here's our triangle for the first one. And this is our 90-degree angle, our right angle. So we have 34 centimeters and 15 centimeters. And we want to know this side. So what I recommend you do when you work with the Pythagorean theorem is just, you can write yourself a little reminder of which side's which. So what side are we looking for, A, B, or C? We're looking for C. That's the hypotenuse, the longest side. So I'm just going to say that's C. The A and the B, it doesn't matter. We can call either one of the others A and B. So I'll just call that one A and that one B. And we know that A squared plus B squared equals C squared. So 15 squared plus 34 squared equals C squared. And I can write this equation the opposite way also. I can say C squared equals A squared plus B squared, and I could say C squared equals 15 squared plus 34 squared. It doesn't matter which way I write this equation. It just depends on you and how you want to do it. I usually keep the thing that we're trying to find on the left, but you don't have to do it that way. So 15 squared is 225. If I plug that in my calculator, 34 squared is 1156. And that equals C squared. I'm going to add those together. So 1381 equals C squared. Undo the square by taking the square root. And I get about 37.16 is what C equals. And my units would be in centimeters. So C is about 31.16 centimeters. Questions on that example? Okay. Let's look at one where we're not trying to find C, where we have to do a little more work and find a different side. So for this one, here's our triangle. So let's say my triangle is set up this way, and I want to find this side. So which side on this triangle is the hypotenuse? Which side is going to be C? 18, the longest side. I can put A or B either place here. What do we want to call 7? A or B? A, call it A, and B. So we're looking for B here. So I'm going to write my equation. 7 squared plus B squared equals 18 squared. So I get 49 plus B squared equals 18 squared. I'll plug that in my calculator, and I get 324. I want to get B by itself, so I'm going to subtract 49 from both sides. And I get B squared. 324 minus 49 is 275. Take the square root to finish to get B, and I get B equals, and I take the square root of 275, and I get about, I'm going to put a little squiggly equal for approximate, 16. I get about 16.6 units. I didn't have any units here, so I'm just going to say 16.6 units, since we're solving for a length. So we just plug in the numbers that we have into our equation and solve for the one that we're looking for. Questions? All right, let's go a little further with the Pythagorean theorem. We're going to talk about the converse. So how do we, at the beginning we said if we have a right triangle with sides A, B, and C, then a squared plus b squared equals c squared. We want to find form the converse. What do we do to form the converse of an if-then? Switch the if and then, switch the order. So for the converse, we're going to say if a squared plus b squared equals c squared for a triangle with sides A, B, and C, then the triangle, I'll use a little shorthand here, the triangle is a right triangle with hypotenuse C. So the Pythagorean theorem works either way. If we have a right triangle, we know that a squared plus b squared equals c squared. And if a squared plus b squared equals c squared for a triangle, that guarantees us that our triangle is a right triangle and c is our hypotenuse. So the kind of problem that you'll see using the converse, and we've done some problems like these already, would say, is a triangle with sides 5, 12, and 13 is this a right triangle? So what this question is asking us is, does the Pythagorean theorem work? Does it work for these numbers? That's what the question is asking us. When it says, is this a right triangle, it's saying, does the Pythagorean theorem work for these numbers? So we're going to try out the Pythagorean theorem on these numbers. So which side, 5, 12, or 13, which side is going to be C? 13. The longest side has to be C, so I'm going to put this as C. I'm going to say this is A, and this is B. It doesn't matter which other one's A and B. 13, the longest one always has to be the hypotenuse, C. So I'm going to say, we want to say, does 13 squared, and I'm going to put a question mark, does 13 squared equal 5 squared plus 12 squared? That's what the question is asking us. Are these equal? Well, 13 squared is 169. 5 squared plus 12 squared is 25 plus 144, which equals 169. They are equal, so the answer is yes. This is a right triangle. If they were not equal, we would say no, it is not a right triangle. They have to be equal for it to be a right triangle. So that's how the converse of the Pythagorean theorem works. If we know that a squared plus b squared equals c squared works, that guarantees us that the triangle is a right triangle. Questions on that one? All right, the last thing we want to figure out today. If it's not a right triangle, if the Pythagorean theorem doesn't work, what kind of triangle is it? Is it obtuse? Is it acute? If the Pythagorean theorem doesn't work with our side lengths, what kind of triangle is it? For that, we are going to use the Pythagorean inequalities. And the Pythagorean inequalities tell us if the Pythagorean theorem doesn't work for our sides of our triangles, what kind of triangle do we have? We know we don't have a right triangle, so what kind do we have? So we're going to say we have a triangle ABC. And C is the longest side. If a squared plus b squared equals c squared, well, we already know this one. What kind of triangle does this tell us that we have? This tells us that we have a right triangle. So this is saying the Pythagorean theorem does work, so we have a right triangle. If c squared is greater than a squared plus b squared, c squared is bigger. Triangle ABC is an obtuse. Obtuse triangle. And what that means, what obtuse means, is it looks like this. So this angle is bigger than 90 degrees. And the last one is if c squared is less than a squared plus b squared. Triangle ABC is an acute triangle, and an acute triangle is harder to draw than an obtuse triangle, so there would be an acute triangle. All of our angles are smaller. Is that acute? That angle looks bigger than 90 degrees. I have a hard time drawing acute triangles. That looks like a right triangle. There, that would be an acute triangle. All of our angles are less than 90 degrees. And the way I think of this one is I use my hands. So if c squared equals a squared plus b squared, my hands are at a 90 degree angle, I have a right triangle. If c squared is bigger, then my hands open up further, and I have an obtuse triangle. If c squared is smaller, I open my hands up less, and I have an acute triangle. So a squared plus b squared equals c squared, I have a 90 degree angle between my hands. C squared is bigger, my hands open up further, I have an obtuse triangle. C squared is smaller, my hands open up less, and I have an acute triangle. That's the way I think of the Pythagorean inequalities. So these tell us what kind of triangle we have based on what we know about c squared and a squared and b squared. So let's look at some examples of these inequalities. Any questions on the inequalities? All right. So the type of question you might see is, the way I'm going to say it is, what kind of triangle? And what I mean is it right? Is it obtuse? Is it acute? So my sides, we'll do a couple of examples. My sides are 14 inches, 7 inches, and 9 inches. So for this triangle, which side is going to be C? Which side is going to be C? 14. It has to be C. I'm going to call that one A, that one B. It doesn't matter for A and B which one I label. So I'm going to say, I'm going to compare C squared to A squared plus B squared. So 14 squared equals 196. 7 squared plus 9 squared is 49 plus 81, which is 130. So C squared is greater than A squared plus B squared. So what kind of triangle is it? This is obtuse. C squared is bigger. My hands have to open up further. So I have an obtuse triangle. So okay, one last example, and then we'll talk about our picture here on the front. So we have sides 2 feet, 3 feet, and 3.5 feet. So which side is going to be C here? The biggest side has to be C, so it has to be 3.5. C. I'll call that one A, that one B. These two I can put in either order. So 3.5 squared is 12.25. 2 squared plus 3 squared is 4 plus 9, which is 13. So C squared is less than A squared plus B squared. So what kind of triangle does that give us? This gives us an acute triangle. So the Pythagorean inequalities tell us if we don't have A squared plus B squared equals C squared, do we have an obtuse triangle, do we have an acute triangle? If A squared plus B squared equals C squared, that guarantees us that we have a right triangle. All right. Any questions on Pythagorean theorem? All right, let's talk about that picture that's on the front there, that tree. So and this, you don't have to write this down. This isn't part of the notes. It's not something that I'm going to ask you questions about. I find this kind of thing really interesting, and I thought some of you might also. So one of the ways to think about the Pythagorean theorem, here's my right triangle. Let me ask a question before we go on here. If I have a square, I'm going to draw a little square over here, and this side of the square is A units. The length is A. What is this side of the square if this side is A? That side is also A. What is the area of this square? Base times height, right? A times A, or A squared. Well, if this side of my triangle is A, this is B, and this is C, one way to think about the Pythagorean theorem, and the way the Greeks thought about the Pythagorean theorem, is that if I make a square on this, and I know my squares aren't going to be perfect, if I make a square on that side of the triangle, and I make each side A, this area is A squared. And if I make a square on this side of the triangle, and each side is B, then the area of that square is going to be B squared. And if I make a square on the hypotenuse, like so, then the area of that square, each side is C, so the area of that square is going to be C squared. So one way to think about the Pythagorean theorem is that the area of this triangle plus the area of this the area of this square plus the area of this square equals the area of this square. A squared plus b squared equals c squared. So what we're doing on this, and let me start this up because I have a nice little animated demonstration. What the picture was there at the beginning was a tree that we can make using this idea with the Pythagorean theorem. Takes just a second to come up. There we go. So what we've got here is a triangle. Here's my triangle, and here are the squares that I've drawn on either side, on each side. And a squared plus b squared equals c squared. So what I do with with the smaller squares that I draw is I draw a smaller triangle on each side of that square, and then draw the squares on the side of that triangle. What we're going to do is repeat this process. So now I'm going to draw triangles on each of these sides, and then draw the squares. So let me do this. So we do this. We repeat that process. Draw the triangles and draw the squares. Now we'll repeat it again. Draw the triangles and draw the squares on the sides of the triangles, and draw the triangles. We do another step, and we end up with this tree. Now the branches of the tree kind of overlap, but that's where this picture comes from, is drawing these squares and triangles and more squares. So it turns out this is a fractal. And what fractal means is I have this shape. Each of these is a smaller copy of the original shape. Each step is a smaller and smaller and smaller copy of the original shape. And you can keep going for as long as you want. And this tree turned out nice and symmetrical. If we make the triangle less even, so these two sides aren't necessarily the same length, then we get our tree turns out to be kind of curvy. And all we're changing here is the shape of the triangle that we start on the one side that we start with for our squares. But we're doing the same thing. We're drawing the squares and the triangles, and we get this curvy shape. And we just get more and more and more copies on each branch of the curvy shape. So, and this turns out to be a fractal because each of the smaller pieces is a copy, just a smaller copy of the original, and it just gets smaller and smaller and smaller. So I just think this is really, really interesting. And what inspired me to look at this, to look at this to show you guys, is I get this calendar every year that has pictures that have to do with math. And let me see if I can find it here. There it is. So this is a guy that he made that tree out of pancakes. So this is a pancake, and he made this fractal tree pancake. That's what inspired me to find this to show you guys. This pancake. So anyway, I just thought you guys might find that a little bit interesting. All right, let's go over the last night's homework. Let me write down tonight's homework so I don't forget. I think I forgot last class. Homework for tonight, page 326. Number 8 through 30 even, and then 40 through 48. I passed out the math box 17. That will be due next week on block day.